question is, which integers are the sum of two rational cubes? It's well known which integers are the sum of two rational squares, namely those integers in whose prime factorization all primes that are 3 mod 4 occur with even exponent. And it's well known that such integers that are the sum of two rational squares therefore have density 0. In fact, we even know the asymptotics of the set of numbers that are the sum of two rational squares. Up to x, it's about x over square root of log x times a constant. So they have density 0 in the set of integers, the numbers that are the sum of two rational squares. And moreover, it turns out, by the local global principle, both for integers and for the rational numbers, that an integer is the sum of two rational squares if and only if it's the sum of two integer squares. And a number is the sum of two integer squares or the sum of two rational squares precisely when there's no local obstruction to being so. Okay, so that's the case of squares, sum of two rational squares. In contrast, the integers that are the sum of two rational cubes doesn't seem to follow any simple pattern. So here are first several integers that are the sum of two rational cubes. It looks like most numbers up to 35 are, about 22 out of the 35 are the sum of two rational cubes. They don't seem to follow any simple pattern. And in particular, it hasn't been known whether the set of numbers that are the sum of two rational cubes has strictly positive density or not, or whether the density is strictly less than 1 or not. Does this set of numbers that are the sum of two rational cubes, does it have positive density? And does it have density that's strictly less than 1? So these have been questions whose answers are unknown. And in contrast to the situation for squares, it's actually possible for an integer to be the sum of two rational cubes, but not the sum of two integer cubes. The smallest example being, so this is unlike the case for squares, but for cubes it's possible to be the sum of two rational cubes, but not the sum of two integer cubes, the smallest example being 6. So 6 turns out is 17/21 cubed plus 37/21 cubed. But it's easy to see that it's not the sum of two integer cubes. One more thing that's in contrast to the case of squares is that there's never any local obstruction for an integer to be the sum of two rational cubes. So all integers are locally the sum of two rational cubes. There's no congruence obstruction. And therefore, proving results on the density of the set of numbers that are the sum of two rational cubes must require global arguments. Local arguments cannot suffice because there are no local obstructions for any integer to be the sum of two rational cubes. The question I want to ask in this talk is, the set of numbers that are the sum of two rational cubes, does it have positive density? And does it have density strictly less than 1? We can state our main results now. So this is, again, joint work with Levent Alp and Ari Shnidman. And what we prove is that when integers are ordered by their absolute values, a positive proportion of integers are actually the sum of two rational cubes, and a positive proportion are not. So the density of integers that are the sum of two rational cubes is strictly between 0 and 1. And more precisely, we prove that the set of integers that are the sum of two rational cubes has density at least 1/6, and the set of integers that are not the sum of two rational cubes has density at least 1/6. So the set of integers that are the sum of two rational cubes is at least, I should have said 1/12, and the set of integers that are not the sum of two rational cubes is at least 1/6. We actually get lower bounds on these densities. Okay, so that's the theorem that I want to sketch a proof of today. And please feel free to interrupt if anything is unclear. Yeah, it's okay to allow negative. If a number is a sum of two rational cubes, then if you just negate the cubes, then the negative of the number is also the sum of two rational cubes.
When you write, when you write n as p cubed plus q cubed, is p allowed to be negative?
That's right. Yeah, a cube is allowed to be negative. Yeah.
Okay, thank you.
Any other questions on the statement?
You keep using the word density. Do we know there is a density?
Oh, no, we don't. Yeah, I keep saying density, but I do mean the limit of the density. That's right. So the limit of the density of the limit of the proportion of integers that are the sum of two rational cubes is at least 1/12, and the limit of the density, limit of the proportion of integers, right, as you let the bounds go to infinity, that are not the sum of two rational cubes is at least 1/6. That's right.
Yes, another question. So is it believed that if you don't allow negatives in your P and Q for cubes. Do you think that will give a different answer?
Yeah, good question. Yeah, I'm not sure. I'm guessing maybe no, but I have to, yeah, I have to think about this.
Thank you.
Great question, thanks. Okay, any other questions about the statement? Okay, great. So I'll talk a little bit about how we prove this. So the theorem is equivalent to the statement that in the family of cubic twists, x cubed plus y cubed equals n. So those are the twists of the Fermat elliptic curve. At least 1/6 have rank 0. Right? So those are the ones that won't have any solutions, and at least 1/12 have rank 1. These curves don't have any torsion once n is big enough, and so the question of whether there are solutions amounts to whether the curve has rank 0 or rank 1. And so what we're proving actually is that in this family of cubic twists of elliptic curves, a positive portion have rank 0 and a positive portion have rank 1. More generally, we can consider general families of cubic twists of elliptic curves. So any such cubic twist family can be expressed as a family of Mordell curves, y squared equals x cubed plus dn squared, where d is fixed and n varies. So any such cubic twist family of elliptic curves can be expressed in this form, y squared equals x cubed plus dn squared, where d is fixed here and n varies. So that's what a general family of cubic twists looks like. And it turns out that the elliptic curve x cubed plus y cubed equals n can be expressed in Weierstrass form as y squared equals x cubed minus 432 n squared. And so this family, the sum of two cubes family of elliptic curves, right? This cubic twist family corresponds to the case of the general cubic twist family where d is negative 432. Okay, but in general, we can fix any d, and we can look at this family as n varies, and we can ask, do a positive proportion of those have rank 0, and do a positive proportion of those have rank 1? And that's actually the theorem that we prove. We prove it for any d. So we prove that if you fix any d not equal to 0, then when n varies, ordered by its absolute value, at least 1/6 of the elliptic curves in the cubic twist family, y squared equals x cubed plus dn squared, have rank 0, and at least 1/6 of the curves with good reduction at 2 have rank 1. If you take the special case where d is negative 432, you get the result I stated on the previous slide about a positive portion of integers being the sum of two cubes and a positive proportion. Okay, so this is actually the theorem we prove. In a cubic twist family, a positive portion have rank 0 and a positive portion have rank 1. That's what we aim to prove. And just some history about this family. So the cubic twist families y squared equals x cubed plus dn squared, where d is fixed and n varies, have traditionally been studied via the Selmer groups associated to a natural isogeny that takes e d comma n to e minus 27d comma n. Defined over Q, it's a 3 isogeny, often called square root of minus 3 because it corresponds to complex multiplication by square root of minus 3 over the complex numbers. If there is this isogeny, this allows one to determine the 3 Selmer group of any such curve using this 3 descent, the square root of minus 3 descent. And in 1879, Sylvester used the square root of minus 3 descent, and also Selmer in 1951 took this much further. And what they showed is that the 3 Selmer rank of x cubed plus y cubed equals p for p of prime is 0, and therefore the rank is 0 for such primes, if p is 2 or 5 mod 9. And the 3 Selmer rank is 1 if p is congruent to 4, 7, or 8 mod 9. And so in these special cases of primes that are 2, 5, 4, 7, or 8 mod 9, we know what the 3 Selmer rank is, and it's either 0 or 1. And if the 3 Selmer rank is 0, therefore it has rank 0, and so there are no solutions. And if it has rank 1, then the parity conjecture should predict that they actually have rank 1. And so when p is 4, 7, or 8 mod 9, we expect that there should be solutions. So this is called Sylvester's conjecture. Well, the 0 part is clear, but the case where 3 Selmer rank 1 should imply rank 1 uses the parity conjecture, and so that the fact that x cubed plus y cubed equals p has solutions when p is 4, 7, or 8 mod 9 is called Sylvester's conjecture, a proof of which was recently announced by Daniel Kritz. Okay, so that's the case of primes. And when primes are not of this form, then the 3 Selmer rank is 2. And so we can't make any conclusions in that case about whether P is the sum of two cubes. So that's the case of primes, but what I want to note is that the square root of minus 3 September group is not very useful in studying x cubed plus y cubed equals n when n has many factors, because the size of the square root of minus 3 September group tends to grow with the number of prime factors of n. So that's why they were looking at the case where n is prime, where the 3 September group stays small. But once n is allowed to be arbitrary, then studying the square root of minus 3 September group is not very useful in understanding solutions to x cubed plus y cubed equals n. And in fact, we make this observation precise. We show that if you average over all n the size of the 3 September group of x cubed plus y cubed equals n, that's actually infinite. So the average size of the 3 September group across this family of cubic twists is actually infinite. And so one can't use that to show that lots of integers n are not the sum of two rational cubes, or that they are the sum of two rational cubes. The 3 September group doesn't really help for general n, even though it did very well for primes. So we need another way of approaching this that's not the traditional one. So 3 September group is not useful. So what we do instead is we determine the average size of the 2 September group. So we approach the problem instead via parameterization of and a determination of the average size of the 2 September group of elliptic curves in any cubic twist family, since the 3 September group blows up. And what we show is that the 2 September group doesn't blow up. It has a finite average size, and we use this theorem on the average size of the 2 September group to deduce that a positive proportion of the curves have 2 September rank 0, and therefore a positive portion of integers are not the sum of two rational cubes. And then we show a positive portion have 2 September rank 1, and that can be used to then show that the curves in fact have rank 1, implying that a positive portion of integers are the sum of two rational cubes. So two ingredients in this deduction are the P Parity Theorem of Nekovar and Dockschitzer, which say that the parity of the rank of the P September group agrees with the parity of the actual rank, and a P converse theorem of Brungel and Skinner, which implies that if the P September rank is 1, then the rank is actually 1 in certain cases. So I'll explain this in a little more detail. So here's a sketch of the proof that a positive portion of integers are, and respectively are not, the sum of two rational cubes. So the first step is parameterizing two September elements of elliptic curves in any cubic twist family by certain integer points on an SL2 cross SL2 invariant quadric hypersurface in the space of triply symmetric 2 by 2 by 2 by 2 matrices. So these four-dimensional matrices, we look at triply symmetric four-dimensional matrices. SL2 cross SL2 naturally acts on such triply symmetric 2 by 2 by 2 by 2 matrices. And there's an invariant quadratic form under that action. And if you set that equal to 0, and you look at the integer points on there, it turns out those parameterize two September elements of elliptic curves in any cubic twist family. And I'll explain this in more detail in a moment. Once you have a parameterization of two September elements by such integer points on a variety, we then combine geometry of numbers methods with the circle or the delta method, which is most readily usable in the form that was written about by Heath Brown. So since we're counting points on a quadric, we can use the circle method to count integer points on this quadric, but we don't want to just count in a round ball on this quadric, the integer points. We actually have to count points in a fundamental domain for the action of this group. And so a combination of geometry of numbers and the circle method allows us to do. And once we have that point count, then that allows us to determine the average size of the two September group of EDN, where D is fixed and N is varying. Okay, so that allows us to determine the average size of the two September group in any cubic twist family. And what we find is that the average size of the two September group is 3, just like it is for the universal families of elliptic curves. So not infinite, but only 3. So that's very helpful. But just knowing that the average size is 3 is not enough to deduce that a positive portion of integers are the sum of two rational cubes and a positive portion are not. In order to deduce that, we have to carry out an analysis of root numbers in the family of cubic twists, EDN. And we prove that these root numbers are equidistributed. And once we know that the root numbers are equidistributed in any cubic twist family, then we can apply the P Parity Theorem and the P Converse theorems to show that many of the curves have to actually have two summa rank 0 and therefore rank 0, and a positive portion have to have two summa rank 1 and therefore rank 1. And then that, in the case of d equals minus 432, then this rank 0 case implies that a positive portion of integers are not the sum of two rational cubes, and the rank 1 case allows us to deduce that a positive portion of integers are the sum of two rational cubes. Okay, so that's a sketch of the whole proof, and now I'll give a little more details on each step. So first I'll talk a little bit about this parameterization of two Septembre elements, because that is sort of what this is all based on, at least on the algebraic side. Okay, so what do 2 by 2 by 2 by 2 matrices have to do with elliptic curves? So this is joint work with Wei Ho. So let K be a field with characteristic of K not equal to 2. And let A be a 2 by 2 by 2 by 2 matrix with entries in K. Okay, so it's this four-dimensional matrix, 16 entries, lying in K. Such a four-dimensional matrix, what can you do with it? Well, we can view A as a quadrilinear form on a product of four two-dimensional vector spaces, W1 through W4. So let's view A as this quadrilinear form on this product of four two-dimensional vector spaces over K, W1 through W4. And now let's consider the set C12 of K, given by the set of pairs W1 comma W2 in big W1 cross W2, such that if you plug in, so sorry, A and H are the same. H is the quadrilinear form corresponding to the matrix A. So let's look at C12 of K, which is the set of all pairs W1 comma W2 and the product of just the first two factors, W1 cross W2, such that if you plug in those two vectors into the first two coordinates of this quadrilinear form, right? If you plug in an element from W1 and W2, you get a bilinear form on W3 cross W4, which is a 2 by 2 matrix, and so you can ask, is that determinant 0? Right? So we're going to look at the set of all pairs W1 comma W2, such that if you plug it into this quadrilinear form, you get a 2 by 2 matrix or a bilinear form whose determinant is 0. Okay, so we can consider that set of pairs in the first two coordinates, such that if you plug them in, the bilinear form that remains has determinant 0. So that's going to be called C12 of K, and that naturally lies inside P of W1 cross P of W2, P1 cross P1. Well, since it's defined by the vanishing of this determinant, which is a degree 2 function in each of these coordinates, C12 is a by degree 2 curve inside P1 cross P1, which generically is a smooth genus 1 curve inside P1 cross P1. And so given a 2 by 2 by 2 by 2 matrix, it naturally spits out a genus 1 curve inside P1 cross P1 by just looking at the pairs that you can plug in the first two coordinates that give you determinant 0 in the other two coordinates. And so in this way, we obtain a genus 1 curve in P1 cross P1. In fact, we obtain 6 genus 1 curves in P1 cross P1 because we didn't have to do that just with W1 and W2. We could have done the same thing with W1 and W3. Look at the pairs in W1 cross W3 that give you determinant 0 in these two coordinates, W2 and W4, and so on. So you can just pick any two coordinates. And so in this way, you obtain 6 genus 1 curves, Cij, in P1 cross P1. Namely, a set of points in Wi cross Wj, such that if you plug them in, you get something of determinant 0. So this gives us 6 genus 1 curves in P1 cross P1. And now we can ask, are these curves isomorphic? How are they related? And it turns out, well, they all are isomorphic, but not canonically so. Let me explain that. So let's start with the C12 inside P1 cross P1. Then we just observe that the curve C12, which is in P of W1 cross P of W2, actually naturally maps into P of W1 cross P of W2 cross P of W3. The reason being that, okay, C12 is defined as a set of pairs such that if you plug them into the quadrilinear form, you get determinant 0. But if you have determinant 0, that means it's a 2 by 2 matrix with a kernel. So given W1, comma W2, and C12, since when you plug in W1 and W2, you get something singular as a bilinear form, you can take the kernel of that singular 2 by 2 matrix in W3, right? And generically, it'll be a well-defined kernel up to scaling. And so you'll get a natural element of P of W3 just by taking the kernel. And so that's a natural map from W1, W2 to W1, W2, W3, where W3 is the kernel of the matrix when you plug in W1 and W2. And so we thus obtained a well-defined element W3 such that if you evaluate the quadrilinear form on W1, W2, and W3, you get identically 0. And so you obtain this genus 1 curve C123 in P1 cross P1 cross P1, which consists of the set of vectors W1, W2, W3, right, in the vector spaces W1, W2, W3 respectively, such that when you plug in those 3 vectors into the quadrilinear form, you get identically 0. And that's the genus 1 curve in P1 cross P1 cross P1. And so we call that C123. And of course, the projection of C123 onto just the first 2 coordinates gives an isomorphism onto C12. Because, right, when we started with C12, we just took the kernel in the 3rd coordinate, and that's how C123 was defined. And so now if we just project back onto C12 by forgetting that 3rd coordinate, we get an isomorphism onto C12. And so therefore C123 provides us with explicit isomorphisms among the 3 curves C12 by projection onto C13 and onto C23. And so therefore C12, C13, and C23 are all isomorphic in a natural way, right? To get the isomorphism from C12 to C13, right, you unproject onto C123, right, by taking the kernel, and then you project onto C13. And so that's a map from C12 to C13. And so in that way, Cij, Cijk, and Cky are all isomorphic by projection and unprojection. And so in that way, all the Cij are isomorphic. And so what this means is that it suffices to just keep track of these Cijk. Right? So we have 4 such curves Cijk, C123, C124, right? C134, C234. So they're just 4 Cijks that we have to keep track of as genus 1 curves inside P1 cross P1 cross. We have the curve C123. We similarly have curves C124, C134, and C234, and P1 cross P1 cross P1. And these are just defined in the same way. What are the vectors in W1, W2, and W4 such that if we plug it into the quadrilinear form, we get identically 0. We get all these 4 curves, C123, C124, C134, and C24 are naturally isomorphic, right? Because from C123, right, you can project onto C12 and then unproject onto C124 by taking the kernel in the 4th direction. So you get a natural map from C123 to C124. And so you have a natural set of maps among all 4 of these genus 1 curves in P1 cross P1 cross P1. But what's crazy about the situation is that you have these natural isomorphisms, but they don't all commute with each other. So in other words, if you go around a triangle of isomorphisms, it turns out that gives you an involution on the genus 1 curve. And if you go around some quadrilateral, start here, say, and go around some quadrilateral, it's a product of 2 involutions, which is actually translation by a point on the Jacobian of the genus 1 curve. So these maps don't all commute with each other. And one can work out, well, what happens when you go around various cycles starting at C12. So I won't go through all the details, but I'll just say, if you go around a triangle, it turns out it's an involution on the genus 1 curve. And if you go around a quadrilateral starting at one of these 4 curves, it turns out that's translation by a point on the Jacobian.
Hi, Manjul.
Yeah.
Just a quick comment. All the talks are scheduled for half an hour. So it's just noticed that you on slide 70-something of 170. So.
I thought the talk was an hour, so that's why I'm only halfway through.
Okay.
Oh, okay. Well, then, how much time do I have?
You can certainly take a few more minutes, don't worry, but
Okay.
you might not be able to get through 100.
No. I'll only get through half of them. So, okay, I'm sorry about that.
No worries.
Okay, well, so I'll just state. So we had those triangles and quadrilaterals of isomorphisms, and they correspond to translation by points on the Jacobian. And it turns out you get 3 different points on the Jacobian that you can translate by just using that 2 by 2 by 2 by 2 matrix. And so the theorem is that there's a canonical bijection between 2 by 2 by 2 by 2 matrices and isomorphism classes of a genus 1 curve, a degree 2 line bundle, and 3 points that sum to 0, Jacobian of the genus 2 curve, on the genus 1 curve. And it's the fact that you're getting these degree 2 line bundles, in other words, maps to P1 that correspond to 2 September elements. So, okay, so I guess that's all I'll say on the algebraic side. So how much time should I take, James?
Maybe 5 minutes.
5 minutes? Okay. Okay. So one last thing I'll say is that these on this parameterization is that the action of GL2 cross GL2 naturally on these triply symmetric 2 by 2 by 2 by 2 matrices. There are two polynomial invariants. One is of degree 2 and one is of degree 6. And we can call them A1 and A3. And it turns out that the Jacobian of the curve C that comes from a 2 by 2 by 2 by 2 matrix can be expressed in terms of those invariants for the group action. Namely, the Jacobian is given by this curve. Y squared equals this degree 2 invariant times xy plus the degree 6 invariant times y equals x cubed. And so all I want to note is that to get the curves that are cubic twists, notice that if A1 equals 0 and you complete the square here, then you get y squared equals x cubed plus tn squared. And so that's how you get cubic twists from this family by setting this degree 2 invariant equal to 0. And so if we're trying to show that the average size of the 2 September group is 3, all we have to do is count points where A1 is equal to 0, where this quadric is equal to 0 on the space of 2 by 2 by 2 by 2 integer matrices. And so that's where the circle method comes in. But we have to do the circle method in a different way because we're not just counting in a compact region, but we have to count in a region that's a fundamental domain for SL2 cross SL2 Z. Okay, so that's the whole proof, and that's all I'm saying on all these slides. What allows us to show that the average size of the 2 September group is 3. But now to deduce that a positive portion of curves actually have 2 September rank 0 and 2 September rank 1, we actually have to know that these curves have equidistributed root number. And that's something that we're able to show using the Selberg-Delange method. So this is actually something that was predicted by Poonen and Raines, that if you go across all elliptic curves, if you just restrict to those that have positive root number, the average size of the 2 September group is 3. And if you restrict to just those that have negative root number, the average size of the 2 September group is 3. And that's not something we know for general elliptic curves, but that's something we're able to prove in these cubic twist families. That half have root number plus 1, half have root number minus 1, and the average size of the 2 September group stays 3 for both of them. And once you know that the average size is 3 for both of them, and that's what this theorem is saying, is that even when the root number is just plus 1 or just minus 1, if you restrict to those, average size of the 2 September group is 3. And once you know that the average size of the root number is 3, both for positive root number curves and for negative root number curves, then we can apply the P Parity Theorem, which states that the 2 September rank must be consistent with the root number. So across the root number plus 1 curves, the 2 September group size will always be an even power of 2. That's what the P Parity Theorem says. And so across the root number plus 1 curves, the 2 September group size is either 1 or 4 or 16, and so on, just the even powers of 2. And if the average of these numbers is going to be 3, then a positive portion of the sizes will have to be 1. In other words, a positive portion of curves will have to have 2 September rank 0, and therefore rank 0, and therefore a positive portion of integers are not the sum of 2 rational cubes. Similarly, for the root number minus 1 curves, the 2 September group size will always be an odd power of 2. So in other words, 2, 8, 32, and so on. And again, if the average of a set of these numbers is going to be 3, then a positive portion will have to have size 2. In other words, a positive portion of curves will have to have 2 September rank 1. And if we know that a positive portion have 2 September rank 1, then under certain technical assumptions, the P-converse theorem of Burungale and Skinner allows us to conclude that a curve has rank 1 if it has 2 September rank 1. And so that's why we're able to show that as n varies ordered by absolute value, at least a sixth of elliptic curves EDN with good reduction at 2. This good reduction of 2 condition comes from Burungale and Skinner's technical assumption that they need to show that if a curve has 2 September rank 1, then it actually has rank. And so the theorems are that as n varies ordered by absolute value, at least a sixth of elliptic curves EDN have 2 September rank 0, and thus rank 0. N varies by absolute value, at least a sixth of elliptic curves EDN with good reduction at 2 have 2 September rank 1, and therefore rank 1. Okay, and so a positive portion of cubic twists have rank 0, and a positive portion of cubic twists in any cubic twist family have rank 1. And so in particular, if you restrict to the case d equals minus 432, we get the corollary that when ordered by absolute value, a positive portion of integers are the sum of 2 rational cubes, and a positive proportion are not. And there are many other corollaries like this because many cubic twist families are of interest. So for example, another classical question, if you look at those integers that are the product of 3 rational numbers in arithmetic progression, that's also turns out to be a cubic twist family. And so another corollary is that when ordered by absolute value, a positive proportion of integers are the product of 3 rational numbers in arithmetic progression, and a positive proportion are not. So the density, again, is strictly between 0 and 1 for those integers that are the product of 3 rational numbers in arithmetic progression. And so on. So lots of classical questions like this. So I'll stop there. Thank you so much, and happy birthday, Andrew. And sorry, I should have asked how long my talk is supposed to be. Apologize.
No, thanks a lot, and Manjul, and no worries about, sorry for the miscommunication about their length. So any questions for Manjul? Can I please also remind everyone to move their mic round to them and to make sure their mic's on for when they ask a question so it's recorded correctly. Yeah, Terry?
Hi, Manjul. Is it expected that 50% of these elliptic curves have rank 1 and 50% rank 0 as usual?
Yeah, that's exactly what's expected. That would have been on this slide had I had the time, but yeah, exactly. So yeah, natural to expect that a density of 1/2 of all integers should be the sum of 2 rational cubes because we expect in a cubic twist family, half should have rank 0 and half should have rank 1. That's what we would expect. Yeah, good question. We checked this computationally. It does seem like when you go out very far, it's approaching 50-50. But there is a bias in the beginning for most integers to be the sum of 2 rational cubes. It's a small integer phenomenon, but yeah, eventually we do expect 50-50, and it seems to be heading in that direction experimentally.
Hi. Okay. I've been wondering, I really like this kind of thing, and I would hear happily you speaking about it for another half hour. My question, though, is going further than your talk. So would it be so hard to go to quadratic families, quartic families, or even a non-isotrivial family of elliptic curve? Would that be possible? Do you plan to do it, or is it out of reach? Or
there's some. The great question. Yeah, there are some isotrivial families that we think we could handle that are not just twist families, because here we did it. We're counting points on a quadric that's equal to 0, but we could have counted, for example, on a quadric where the quadric is equal to 3, and the circle method still applies, and then it's not quite an isotrivial family, and we could count there. So there are a number of other things to try here, and happy to talk about it more with you after. Yeah, but there are definitely other types of families that could be done and handled using this method.
Yeah, I also watched your talk in Cambridge before, so I had the whole talk.
We have a more detailed version.
I mean, do you expect that the full 2 descent can work out and give you 50-50? Does Smith's methods hold any hope here?
Yeah, that is a natural thing to think about next, but this method is so different than Smith's method, and so far we haven't been able to combine them, but that doesn't mean they can't be. That's the next natural thing to think about, but we haven't been able to combine the methods yet.
So look at your theorem obviously applies to ax cubed plus by cubed.
Particular
x cubed plus 2y cubed, which this conference is famous for the number of prime values where x and y are integers.
Oh, you're right.
I'm wondering if you can do the number of prime values where x and y are rational numbers.
That's a great question. Yeah, I'll think about that.
I mean, in general, can you adapt your methods to do some proportion of prime values for binary cubic forms?
Yeah, actually, I guess the binary cubic forms equals p is an elliptic curve, and one could do a 3 descent on those. Yeah, it's possible that one could get
2 descent.
Positive proportions. Yeah, if you set it equal to p, then actually 3 descent could be effective as well.
It doesn't explode.
Yeah. But also doing a prime sieve on these two descent methods, you still get a finite bound on the two-Selmer group as well. So maybe seeing both of them and see how they play off each other could also be very interesting. Yeah, we'll definitely think about that. Yeah, but yeah, both 2 and 3 descent could be applied to those particular curves using this parameterization for 2 descent and then the usual kind of square root of minus 3 descent. Yeah, Smith's methods at the moment don't apply to these kinds of families, so that's why we're only at understanding 2 descent and not the full 2 descent. Yeah, great questions. Yeah, lots of things to think about next.
Yeah, you mentioned at some point you use the Selberg-Delange method.
Yeah.
In which you used it is one where the pole is 0, so you have lots of cancellation. Is that
right? Yeah.
Just a little bit of cancellation would have been okay.
Yeah, that's right. Yeah, I mean, we just need a little bit of cancellation to get to 50-50. Yeah.
Okay, thanks.
He's implying you should use pretentious methods.
Right, to do better. Yeah, maybe.
Any final questions for Manjul? Okay, seeing no further questions, let's give Manjul another round of applause. Thanks a lot, Manjul.
And thanks for all the great suggestions. This was really cool.